Okay, so now let's put together the solutions that we found into linear combinations. So we have discovered that here is the kind of function that satisfies the heat equation differential condition. It will be some function f, not some function, a very specific kind of function, the kind of function that satisfies this, the Laplace eigenvalue equation. F, and it'll be a function of z, and it'll depend on omega. So maybe I can put omega right here. Will there be 1 omega, 2 omegas, 3 omegas, infinitely many omegas? And it could be worse than infinitely many. It could be a continuum of omegas, or discrete omegas, or just a finite number of omegas. They're all very interesting questions. If you think by analogy with linear algebra, you might think, well, maybe a finite number of omegas. And if you realize, well, this is more about n-dimensional, and we have infinitely many degrees of freedom, well, maybe infinitely many omegas. Or maybe it's worse. Maybe it's a continuum of omegas. Maybe any number would work. What I mean by this is that when we solve this equation, we'll discover that we might have 1, 2, infinitely many, or however many omegas. And for every omega, we'll have a possible solution, but for a different omega, we'll have a different f. So they're kind of common pairs. Eigenvalues, eigenvectors, eigenfunctions, eigenvalues, eigenvectors, eigenvalues, eigenfunctions. They come in pairs. So I could label it sub n, thinking there may be, a discrete number of them. But I don't know. So I'm just calling them different omegas. Whatever the value of omega is, there is a corresponding f. That's what I mean here. And then it will get multiplied by e to the minus alpha omega squared t. And the very important coordination is this, right? The omega is shared between them. So when you separate your variables and you solve your Laplace eigenvalue equation, and you get your omega, because that's how eigenvalue equations work, and the f. And we know that it comes from this product, from this kind of product. When you put them together back into the product, it needs to be the same omega. Whatever omega you got for the f, that's the corresponding omega that you will use in t. So that's why this coordination is very important. This form satisfies this equation. And because the equation is linear, we can multiply it by any constant c. It will also depend on omega, because this whole function is whatever omega you get. And then you'll be able to add all of them together, a linear combination, over all possible omegas. And that's your u. So going from the individual form to this linear combination depends essentially on the fact that this is a linear differential equation. And that's what makes it possible. So one kind of an important remark from the linear algebra point of view and history of how this field developed. There's something that we've never done in linear algebra here. If we have infinitely many omegas, then this is an infinite linear combination. Quite possible. So we're back in the calculus world and the world of infinite series, and all of that is perfectly valid. But from the linear algebra point of view, all of the notions of linear dependence and all of those other fundamental bases become more challenging. I wouldn't say more problematic, because many of the analogies carry through, but more challenging when the space is, I'm trying to avoid saying this, but I really can't, is infinite dimensional. And there are infinitely many linearly independent functions which I'm putting together into an infinite linear combination. Calculus welcomes this. It says, oh, great, just what I love, infinite series. But a linear algebra person will be like, okay, let me rethink some of the things I've said before. So for the wave equation, we get a very, very similar thing. But I will write it in a way where you'll say, oh, I think we need to make a little bit of an adjustment. Okay, so I will get, once again, my same solution to the Laplace eigenvalue equation. After all, it's the same. If the domain is the same and boundary conditions or initial conditions, I'm sort of leaving that discussion until later. This will actually be the exact same function, except it gets multiplied by a, I'll put an index here in just a moment, because of course that depends on, did I do sine first or cosine first? Sine, okay. Sine c omega t plus b cosine c omega t. And of course, these depend on omega also. That only matters, and I'll put another multiple out here temporarily, and then now I can add them all together over all omegas that we will find. This is a blueprint, a framework. When we consider a specific function, a specific problem in a specific domain, it will become clarified. And that's what it equals. Okay. So everything went into this. There's lots of linear algebra. The fact that both of these are linear equations, that's what allows us to add them up. Everything's coming together very nicely. It's just that I'll make one note that has nothing to do with PDEs at all. It has to do with trig. But very important. You look at this and you see there are just too many constants. You know, the way these A, B, and C, nice how it worked out, interact, there's just too many of them. Because for a given function, if I multiply these by 10 and in exchange divide this by 10, it'll be the same function. So I kind of put in too many degrees of freedom. So I could deal with it in a couple of ways. Number one, I really don't need this one, because these two do the job for me, right? That's one way to think about it. But another way to think about it is to combine these in a nice way. It's actually maybe the same way of thinking about it, into a amplitude and phase. When you have a linear combination of a sine of an identical cosine, you get another thing that's periodic. And that periodic thing will have its amplitude that obviously depends on A and B. And then it'll be either sine or cosine or something in between in terms of shift. So there's a way to rewrite this that recognizes this. And the thing to do, I'll just focus on this. And I will call it tau for trig, the trig part. The tau can be rewritten like this. You take out the size of the vector AB. So I'm going to factor out the square root of A squared plus B squared. That's how you turn something like this into amplitude and phase. So it becomes square root okay. And now what you see here is we have two numbers that have this nice, very special property. They're sort of part of a Pythagorean triple. This squared plus this squared equals 1. So if this is the cosine of some number, then this is the sine of some number, or if this of some angle. Or if you say this is the sine of some angle, then this is the cosine of some angle. Let's call it the cosine of some angle. So I will just cosine, right? That doesn't matter. What do we want? Do we want sines or cosines? Sine. Doesn't matter. Hold on, let me see what I want. Do I want the shift to be with a plus sign? I'll call it the cosine of some angle. What's a good angle? Beta. So I'll find an angle beta. That pretty much determines beta, doesn't it? Except there are two betas that have this property. Beta and minus beta. So I'll choose the one whose sine equals b divided by the square root of a squared plus b squared. Okay? And then here we have cosine beta sine this plus sine beta cosine this. It's the sine of the sum formula. So this part right here, and this is a much more attractive form because, from a certain point of view, because you have your clear amplitude and the shift, which is called the phase. So maybe a better way of writing it. And now this clearly gets absorbed into C because they multiply each other. So you can write the whole equation. I won't do it here. Well, I'll just put the alternative. Is to take this and to multiply it by sine C omega t plus beta. And now you have your two constants, beta, and all of this depends now on omega. We'll just remember that that may depend on omega because here everything depends on omega. And so now we're down to our two independent degrees of freedom in terms of how we can move functions. This, C is one, and beta is another. And I'll just say one other thing is that from a certain point of view, this is actually a better way of writing it, even though it's less compact, is because it's more true to the spirit of linear algebra. In linear algebra, we like seeing linear combinations of independent functions. And that's what we have here. Here's a function, they're linearly independent, and here's their linear combination. Perfect. So this is more compact, this is more linear algebra. So now you know what solutions look like. Solutions, not solutions, but functions that satisfy these equations. So the next task, when you're actually looking at a specific problem, at a complete, what's called well-posed partial differential equation system, you need to match the initial and the boundary conditions. And how do you do it? Well, you have this certain number of degrees of freedom. They're your C's. In this case, they're just your C's. Am I right? Or is there a missing one? No, that's it. In this case, they're your C's. And in this case, they're your C's and betas. Or, in the alternative way of looking, you ignore this, because that degree of freedom is here, and you can just say A and B, whichever way you prefer. And that makes sense why it's 1 here and 2 here, because this is first order in time, and this is second order in time. So our intuition for how many conditions you need, depending on the order of the equation, works here as well. And I'll just say one last thing about the nature of these solutions without actually dealing with boundary conditions. And then we'll look at a specific problem in one dimension. Hold on one second. And I'll say this. For the heat equation, the higher this frequency, the higher this eigenvalue, the faster the decay. So we'll look at this problem. You can call it, if somebody held a bunch of menorahs, candles, right? The temperature profile would have a very high frequency. And then maybe it'll be warmer in the room because that's where all the candles are. And then you extinguish the candles. So this really high oscillation will die out very quickly. You won't be able to tell how many candles there were or anything like that. That detail goes away immediately. And the fact that it's warmer in the middle and colder on the sides, that will take longer to relax. So the higher the frequency of the spatial oscillation, the quicker the decay. And here what we're seeing is that the higher W, the quicker the oscillation. So on a guitar string, there are some modes. We're about to basically do the guitar string. First for temperature and then for wave equation. There will be some low spatial frequencies and some really high spatial frequencies. Right? The ones that are really high produce very high pitches, because that's pitch right here. The ones that are smoother in space produce lower pitches. So that's the last general thing that we can observe from these general forms.